Okay, hello everyone. So I have shared my screen and I hope you can see the slides. Before we start our lectures today, I just want to say that today I will try to go a little bit faster because we are falling behind of our schedule and I need to cover the material, but it doesn't mean that I'm discouraging you to ask the questions. So whenever you have a question or you are confused, not clear, please uh, send me your question either in text or you can unmute yourself and start talking, okay? So last time we were talking about threads and how the threading support is implemented. We said threading support can be implemented possibly in two ways. Either you can implement threading support at the user level or the kernel level. And then we were basically talking about how the threading support is implemented at user level, right? So uh, we had seen these slides where we said that if you implement the threading support at user level, it is basically implemented in the form of a runtime library because it then provides you it makes your life more comfortable by providing you the functions for creating threads, terminating them, managing and scheduling those threads. So when a threading support or library is implemented at user level, the kernel is unaware of those user level threads and it still treats each user process as a single thread. Uh, and when implemented at user level, so what happens that the runtime, it actually maintains a thread table per process figure here. So it maintains a thread table for each process where it keeps the thread specific information. For example, the content of the program counter registers, program counter, other general purpose registers, and stack pointer, right? Uh, and remember that we don't need the kernel level privileges to read these or to access this information. For example, PC, general purpose register, and stack pointer. So a user library or runtime can do that. Uh, However, kernel still maintains a process table where we have one entry, a process control block for each process currently on the machine. Uh, uh, and the user level library or the runtime, it is responsible for creating, terminating, and scheduling the threads, right? Uh, how the thread scheduling happens at user level if you're implementing a user level thread library, so then we expect a thread that it must release the core on which it is running voluntarily, right? And how it does that, for example, by calling an API or by calling a function. So for example, it can be a function like thread yield, right? So when a thread, for example, this thread running here, when it will, let's say it is running on currently on a core. So here in this figure, we are just showing that a process shown in a circle has multiple threads, and then those threads are user level. But to for this for a particular thread to execute, it needs to be allocated on a core, right? So when it is allocated a core and it is running there, so since these are user level thread and kernel is unaware of their existence, so kernel cannot uh, intervene to schedule the threads. So that's why we expect that these threads voluntarily release the core. And how they do the by executing a thread yield function, right? So when this function is executed, so what happens that this is basically a function in your runtime library, in your runtime or library. So upon execution, the library will runtime will store the information of the calling thread in the thread table, and we know what is the information specific to a thread: program counter, general purpose registers, and the stack pointer, right? And then after that, our runtime will find another thread within the same process that is ready to run, right? And then if it is ready, then it will load its information by looking in the on the thread by looking at its entry in the thread table. It will load its information, which is basically the value of the program counter, register, and stack pointer specific to the thread which we are going to launch or which we are going to start executing, right? And as I said, kernel level pages are not needed for performing these operation, basically reading the value of these registers. So it means that user level, so it means that when we are implementing a threading support at the user level, uh, uh, then we cannot allow concurrent execution of thread. We can allow the concurrent execution of threads, but cannot allow the parallel execution. Why? Because we are saying that a second thread can start as second thread from the same process can start executing only if the previous thread has voluntarily released the core, right? Because the kernel or operating system still treats this application here as a single thread, right? So kernel allocates only one core to this process. Now, but at the user level, there are multiple threads. So, but we cannot run multiple threads on a single core which is allocated by the kernel at the same time, right? So therefore, these threads, they have to voluntarily release it so that another, how to say, another thread in the same process can start executing on the same core, which is allocated by the kernel at the process level, right? So, and the reason for that is the why we cannot run the multiple threads at the same time from the same user process if threading support is implemented at the user level. The reason for that is the same which I have already explained, that kernel allocates the core to a process, and since the library is implemented at user level, kernel still views a process as a single thread, so it gives only single core. So what are the advantages of like implementing that threading support at the user level? One advantage is that we can achieve the portability. So we can support, which basically mean that we can support or we can implement the threads even when kernel doesn't support, provides any support for the thread implementation. So if like kernel is unaware of threads or doesn't have any understanding of the concept of threads, still if we have this user level library, we can still perform threading, and we can if that library is, let's say, available on two different systems, and since it is a user level library, so we can support multi-threading without expecting any how to say background support from the operating system. The other thing is that user level scheduling, that for scheduling and for the context switching, we don't need to trap into the kernel, which basically mean that, as I explained in the previous slide, like if this thread, let's say I'm naming is as thread one, and the other thread, this one, let's say thread two, but they both of them belong to the same process. So uh, who is responsible for scheduling? And remember again, kernel is allocating only one core for a process, but although that process has multiple threads at the user level, right? So now who is responsible for scheduling these user level threads on that single core? It is the runtime system, right? Which is a user level code. It is not a system level code, right? So it's mean that for the purpose of scheduling, are allocating that single core to one of those multiple threads of the same process, we don't need to make a system call. So therefore, the scheduling becomes, we don't need to need any intervention in system. So that's why scheduling becomes less expensive. Remember, whenever we need intervention from the operating system, or a user level user code needs an intervention from the kernel, it's mean that we are switching from the execution of the user level code to the kernel code, and then we need to come back from like switching back from kernel execution of the kernel code to the user level code. So it's like kind of context switch, right? Context switch mean that execution of one entity is taking over the execution of the other. So it is like, as you remember, like we have talked about it, and there was a question also in the exam, context switching incurs our head. So if the scheduling is done all at the user level, so we are not going to incur an intervention from the kernel. So that's why there will be no switching from user level to the kernel level, and scheduling will be less expensive, right? Also, same is true for the context switching, right? So scheduling is like the entity who is performing, who is deciding that which thread will be responsible, which thread is going to execute next. But context switching is like, yes, I have decided that I am going to this thread A by the thread B. So scheduler is done with its with making the decision, but after that, I have to replace thread A with the thread B. So that is context switching between two threads. So it is also expensive, right? If if your kernel is involved. Also, we don't need to make any system call for thread scheduling and text switching, basically for the same reason, because actually these two statements are like, how to say, two different versions of the same thing, right? Since we are not making any system calls, so that's why thread scheduling and context switching will be easier. Will be less expensive, not easier, less expensive. However, the problem with this approach is like implementing the threading support as a user level library is that if one of those threads invoke a blocking system call, or let's say there is a page fault, we will talk about what is the page fault later on. So if one of them make a blocking system call, then it will block whole process. So what does it mean? So let's say these thread 1, thread 2, and thread 3, these are three threads in the process, right? But these are three threads at the user level. Kernel still is looking at this, is doing this process as a single threaded process, right? So if any one of them, let's say thread 1 makes a blocking system call mean that it, remember we have discussed it last time. So let's say make a system call, for example, it says, okay, I want to send data to another thread, and this is a blocking send, right? So the thread 1 gets blocked. So if the thread 1 now gets blocked, now what will happen is that from the kernel's so it is like system call, so it will trap into the kernel. So when kernel will see that, okay, this thread cannot continue its execution for the time being, maybe because it is not able to send the message, or because the receiver is not ready. So what it will do is that it will, because it is unaware of existence of other threads in the user level, so it will replace, it will context switch the whole process. It will suspend the process, which means that all other threads in the same process will also be blocked. They will also be not able to continue their execution. If you have a question at any time point, please go and ask me, okay? So again, this is just a reason why all other threads are blocked, because kernel is not aware of user level threads at all, and treats the process still as a single threaded process. And other problem is that, which I mentioned earlier, that a thread is voluntarily expected to release CPU by invoking thread yield function. So otherwise, other threads never get a turn to run on the CPU, right? And now the problem is that, for example, remember we said that if a process is occupying a core for unusually long time, for example, if it is stuck in a loop, then kernel can intervene and forcefully, how to say, kick out that process from the core, right? How kernel can do this? Because kernel sees a process as a single threaded process, right? So it can keep track of that process. However, these multiple threads within a process, they are at a user level, and they are not visible to the kernel, right? So if one of them gets stuck, right, so there is, kernel cannot see it, and there is no way to like kick out that thread which is, let's say, stuck in a loop from the core. Because for that we need to keep track of the time. So for which we need the timer, but timers are not available in user level code. So user level code cannot access timers directly, right? So which means that the runtime library, which is managing the threads, can have no access to the timers. So it cannot track that, okay, one particular thread is spending a lot of time, or it has exceeded the allocated time budget, so I need to replace it with another user level thread in the same process. So because there is no notion of clock interrupts within a user level process, so that is not possible. So if like one thread is not going to voluntarily release the core, other threads in the same process, they will be starving. Okay, any questions here? Okay, remember we asked the question that how we are going to implement the threading support, like who will be responsible for creating threads, terminating them, scheduling them, doing the context switching, and so on. So the one answer to our question was that we can implement the threading support at the user level. Now the other option is that instead of user level, we can implement the threading support which means the mechanism for all those operations, thread creation, termination, scheduling, context switching, managing resources. We can make kernel responsible for that, right? So if we do that, so how the things look in this, if we make that decision. So then what happens is that a kernel is now aware of the threads which exist within a process, right? So here, for example, you have a process and it has multiple threads. Since kernel is responsible for implementing the threads or managing them, so it maintains a thread table. Remember last time that runtime library was maintaining a thread table, but now kernel is maintaining the thread table. And it's still, in addition to that, it all still has the same process table, which we have seen in previous lectures. So in process table, you have one entry for each process control block. And in thread table, you have one entry for each thread, for all the threads in the system, right? So how threads are created or terminated. So then a user process will invoke a system call to create or destroy a thread. Remember, when threads are in threading support is implemented at user level, we don't need to make system calls to create or destroy a thread. All that is done by a user level library, and kernel is not involved. So what does kernel do? It maintains a single thread table for all threads in the system, not only for, like, it is the thread table is not per process. Thread table is for all threads in the system. And this table is updated on creation or destruction of the threads, right? And each thread table entry holds only thread specific information, which we have already seen earlier, Basically, it is program counter, general purpose register, and stack pointers. The good thing is that if, let's say, now we have these three threads in one process, and if one of them is blocked, let's say it is waiting for some IO, and because it is waiting, so IO is not completed yet. So if it gets blocked, so then kernel, what it can do, it can select any other thread from the same or a different process. So now remember, thread table is for all the processes. So it's mean that in thread table we will have 6 entries, right, in this particular example. Now, if this particular thread is blocked, so now the kernel will look at other 5 entries and see which one of the other 5 threads are ready to run. So it can then pick one of those ready threads. The ready thread which it picks, it can be from the same process, or it can be from the different process. And then it can allow that newly picked thread to run on the core on which this thread was running, which is currently blocked, right? So this is different from user level implementation, where next thread is selected from the same process. In the user level implementation, when a thread of a process voluntarily releases the core, the next thread which the runtime library picks to run is from the same thread, is from the same process. Same process another thread of whom has voluntarily released the core. Any questions? Okay, so what are the advantages? So the main advantage is that if a blocking system call or a page fault happens, so by one thread, it doesn't block all other threads of the same process, right? Right? Why? The reason is because the kernel can see all these threads which are all of these all of these threads of the user level processes, because it is responsible for managing them, and it has an entry for each one of them in the thread table. Also, a thread cannot occupy the CPU forever. Why? Because this time kernel is responsible for managing, and if it finds out that a thread is, let's say, stuck in a loop, and it is for forever, and then it can keep track of the time using timers, and then if it sees that time is exceeded or the allocated time budget is expired, then it can kick out that thread. However, the problem is that when you implement the threading support at the kernel level, so you need to make system call every time when you want to create a new thread, or you want to destroy or terminate an existing thread. And these system calls are expensive. this is different from the user level implementation. When you are doing user level implementation, you don't need any intervention, or you don't need to make any system call for thread creation or destruction. So since thread creation instruction, they are expensive because you need to make the system call. And when you make the system call, first thing is that you are trapping into the kernel, and then when you create a thread, it's mean you are creating a new entry in the thread table. And when you are destroying a thread, you are deleting, or you are removing the entry, its corresponding entry from the thread table, so which takes time, right? So in order to mitigate that latency which is required for creating and destroying a thread, people use an idea or an approach which is named as thread recycling. So what you do is that, let's say when thread one is to need, needs to be is needed to be destroyed, you actually don't remove its entry from the thread table, but you only mark it as not runnable. So you still keep the entry in the table, but you mark it that this entry is kind of deactivated, right? But you don't you don't destroy that entry. uh, and then what you can and you keep all the kernel level data structures for that particular thread which was supposed to be destroyed, and then you reuse them for the next newly created thread. So let's say thread one is to be destroyed, so you just mark its entry as not runnable, and any kernel level data structures which are needed for successfully running a thread, for which were needed for successfully running thread one, you keep them. In future, when there is a request, let's say a request to create another thread two, so what you can do is that you reuse that thread entry, the entry in the thread table, and you also reuse those kernel level data structures instead of like from initializing and preparing them from scratch. So it saves some time. Okay. Remember, we talked about fork in our previous lectures. So if, let's say, when we are saying like, let's say there is a main function. So initially we have a single process. And when in the main function, let's say you are saying x is equal to fork. So a new process will be created, right? So, but there what we were assuming. So let me just draw here. So let's say you have process A and it says fork, so it will create another process will be created which will be child of process A, right? But here we were assuming that both that process A is a single threaded process, right? Now let's say we again have process A, right? I'm now writing A outside, and it has three different threads, right, running at the same time, right? And one of them says fork, or executes the fork. One of those threads execute the fork. So it's mean that we need to create another process B. Now remember, when we say fork, the a new process is created with a distinct address space, but that address space is duplicate of the parent. So in this situation, what does it mean? Like when let's say this thread 3 says fork, right? So when we say duplicate, so should we create all three threads also in the new process, or we should create only the thread which invoke the fork, right? So how to handle a fork by one thread of a multi-threaded process? So there are two options. We can create same number of threads in the child as that in the parent process, or we can create one child, right? Uh, and it depends upon your usage of the basically on what you are going to do after creating a new process, right? For example, if after creating this new process B, after forking, you are saying okay, execute LP, which basically mean load its address space which with the new binary or with the new address space. So then since you are overwriting its address space, it makes no sense to copy over all the threads. You can copy only the thread 3, and then when the execute LP will be executed, so our new binary will be loaded, all of this will be overwritten, right? So it doesn't make sense to copy all three threads. However, if the new process B is not going to load a new binary, then you can copy over in the address space all the three threads, same as in the parent. Any questions? Okay. Okay. So we have talked about implementing the threading support in two different ways, either at the user level or at the kernel level, right? So uh, then there is a question that how can we map the user level threads to the kernel level threads, right? When we say user level threads, it's mean the threads which are part of the application, right? So how those threads are tracked by the kernel level threads. But before going to that, we can ask the question why we even need mapping, because operating system, it can see only the kernel level threads and uses them for the resource allocation, right? So for example, if you have a sorry, for example, if you have a process, right, and let's say our threads are implemented in threading support is implemented at user level. So let's say you have a process here, and you have, let's say, three threads in this process. And again, remember, I'm assuming that threading support is implemented at user level, right? So now there are three threads, T1, T2, T3. But kernel is not aware of their existence. Kernel is aware of only the existence of this process P, right? And which it considers as a single threaded, right? So what it will do is that it will have only one kernel level thread, right? Now, since there is only one kernel level thread, and remember that only kernel level thread can be used by the kernel for resource allocation, right? So what if we want to run T1, T2, and T3? If we want to run them, they also need the resources, right? When we say they also need the resources, for example, they need general purpose register, they need the value, their specific value loaded in the program counter, they need a specific value for their stack pointer and so on, right? So are also other, like for example, accessing uh, any kind of IO devices, right? So are accessing memory, right? So that's why what we need to do is that we need to map these kernel level user level threads to the kernel level threads, right? But how we do the mapping, that is a different question. So here we are just first talking about why we need to do mapping, because uh, we only kernel only, how to say, entertains the kernel level threads for the resource allocation. That's why we need to map user level threads to the kernel level threads, or in a way you can say we need to attach them to the user kernel level threads so that they can actually benefit from the resource allocation. So if a user level thread is not mapped to the kernel level thread, it effectively does not exist for OS. So if it doesn't exist for OS, it's mean OS will not allocate any resources to it. Okay, now what are the different ways of mapping the user level threads to the kernel level threads? So one option is that we can map multiple user level threads to a single kernel level thread, right? Uh, the uh, so what is the advantage? The advantage is that you need to create lesser number of kernel level threads to handle multiple user level threads, right? To handle multiple user level threads, right? But the problem is that uh, if any one of if any one of these threads which are mapped to the same kernel thread, if any one of them is blocked, so because then all other of them will also be blocked, right? Because let's say if currently this T1 is mapped with to the kernel thread, right, and it is executing. So if this gets blocked, then kernel thread will also be blocked, waiting for, let's say, the IO which is requested by this user level thread to be completed. So all these other will not be able to continue. So multiple threads, they will not be able to run in parallel even if you have multi-core system, because only one of them may be in kernel at a time. So this approach was useful in older single core systems, because you had only at like hardware level, let's say you had single core, but at the software level you were writing your program in a by using multiple threads. But since your hardware allows only one thread to run, so what you will do is that you are able to run only one kernel thread, but you allow multiple user level threads to attach with them. So if none of them is, let's say, blocked, so and each one of them is given, let's say, equal amount of time. So let's say you give 5 minutes to each of them. So thread one runs for 5 minutes. So kernel thread handles all the requests for thread one coming from thread one five for 5 minutes, right? Or it take care of thread one for 5 minutes. Then it can take care of thread two for next 5 minutes and so on. It's mean it appears like you have kind of concurrency, right? But this is useful because still by using single cores you can run the multi-threaded application at the user level. Currently, modern systems are not using this approach of mapping multiple user level threads to the kernel level threads. Another approach is that where we do the one-to-one mapping. So each user level thread is mapped to a to its own kernel thread, right? So so here, whenever you create a user level thread, a kernel level thread is also created, which will take care of it, right? So this allows more concurrency than many to one. Why? Because now let's say if you have four cores, uh, so now you can run the four user level at the same time here, right? So if you have four cores, so these four kernel threads are running on those four cores at the same time, and each one of them is taking care of one independent user level thread. However, if you compare it with this approach, right? So let's say you have four cores and you have one kernel thread. So even though you have four cores, you cannot use them because you have only one kernel thread taking care of all four user level threads. So remember, always kernel level threads, they are allocated, they are responsible, or they are allocated the cores for execution. And then they handle in turn the user level threads. They are mapped to user level threads. Now the thing is that uh, since you are mapping each user level thread to a separate kernel level thread, it's mean that uh, at the kernel level, your size of thread table, it will increase, right? So for example, here you will have four entries in the thread table, but in this case, you will have only one entry in the thread table, right? So it's mean that your size of your thread table will increase with number of user level threads, right? So which results in extra overhead. So maybe sometime you need to put a restriction that, for example, these are the maximum number of kernel level threads which can be created, or in other words, these are the maximum number of user level threads can be created because each one of them trigger creation of a kernel level thread. And most modern systems, they actually now use this one-to-one mapping.
And that also makes it so that if you block a thread, it doesn't block all of them, right? Because they're individually linked through the kernel, so they can be recognized.
That's correct. That's correct. So for example, if this one is first one is blocked, all other three, they are independent. They still keep running.
I have a question. If you make like a user thread, right? Since it creates that kernel thread, does that mean it makes a system call? And how is that super expensive or not as much?
Yeah, you need to make a system call and it will become expensive because as I said, that whenever you have any kind of interaction, whenever user level code have any kind of interaction with the system level code, it becomes much more expensive as compared to the case where you don't interact with the operating system. I hope I answered the question. If not, let me know. Okay,
Thank
then
you.
you're welcome. Okay, so another option is that where you can have many to many mapping. So basically, many user level threads or multiple user level threads are mapped to like uh, where multiple user level threads, they are mapped to multiple kernel level threads. This will allow your operating system to create a sufficient number of kernel threads. I am not exactly sure. I didn't go through it in detail, and I'm not exactly sure what does it mean by mapping multiple user level threads to multiple kernel level threads. Does it mean that, for example, let's say this is kernel thread K1, it will take care of, let's say, these four user level threads at, let's say, let's say time duration D1 and a T1, let's say, and then K2 will take care of these four level user level threads for duration T2. I am not sure on that, and I don't want to feed you the wrong information. I can check it and then I can get back to you. Okay. Okay. Uh, yeah, thread libraries. As we said that you can implement, so thread libraries, they are basically provide you functions for creating and managing threads. So these thread libraries, you can implement them both either at user level library or as a user level library or as a kernel level library, which is basically the same thing we have talked earlier, user level support or the kernel level support, right? So if it is a user level support, user level library, all code and data structure needed to implement library exist in the library in user space, right? Which is good thing in one way, and we don't need kernel support for threads. uh, and thread creation and management, it is handled via local functions or calls to the library and not using the system calls. But then again, the disadvantage is like if one of the thread in the process is blocked, then all other threads in the same process get blocked, right? And also, if one thread gets stuck in an infinite loop or doesn't releases the core, then all other threads in the same process, they will stop. They will never get the turn to run or execute. The kernel level library is that where you implement all code and data structure needed to implement the library. You write that code in kernel space and it is executed in the kernel space. So whenever you need to create, destroy or manage the threads, you need to make the system calls. So actually you are asking the operating system to do that on your behalf. So example of these thread libraries are POSIX, Portable Operating System Interface. So actually it is not a library, it is a standard, and then this standard is implemented by different operating systems, right? Other than that, there are also window threads library and Java thread. We are not going to cover that. We will cover only POSIX library or Pthread, right? So Pthreads, it is actually implementation of POSIX standard. It is a standard defined for thread creation and management. Again, this is just a specification, not implementation, right? However, this standard is implemented by different operating system for example, Unix, Linux, and Mac operating system. So which basically mean that all of them support the POSIX or Pthread library, right? So the standard can be implemented either as a user level library or the kernel level library. However, in Linux, this library is implemented, standard is implemented as Pthread library, and it is implemented as kernel level, not as a user level. And this is, as I said, now the approach in most of the modern operating system, that they implement the threading support at the kernel level, which means that whenever user level code need to create a thread or do anything related to thread, they need to make a system call. Okay, so we will talk about pthreading. We will see pthread library, and we will see a complete example of how to create, destroy, and how to use threads using this library, right? So before we talk about that example, let's first uh, understand these two terms, synchronous and asynchronous threading. So synchronous threading is where your parent thread, which basically is the thread which is creating other threads, right? So it must wait for its children threads to terminate before it resume, right? It is same, just like, for example, in your project one module A, what you were doing is that you were forking multiple processes, and then you are waiting for those multiple processes to complete, right? And then the parent process was able to continue, right? So same here. So that is known as, if that is the behavior used by the threads, like for the by the parent thread, then we name it as synchronous threading. Asynchronous threading is that where your parent thread doesn't wait for the children to terminate. It can just create the children threads, and after creating, it can continue with its own execution, right? So both the parent and the children threads, they can run simultaneously and independently. Again, you can again use the same analogy of the processes where you are saying, don't wait for the children processes to complete. You just create the children processes and continue with your execution. Any questions? Okay, so let's have a look at a multi-threading example. So in this example, what we are going to do is that we have a parent thread, which will create children thread, and then it will create for all the children threads. Then it will wait for all the children threads to terminate, right? And it creates basically 4 children thread. So I am just keeping what those children thread are going to do. I kept it very simple because we want to focus on creation and destruction of the are running those children thread, not on focusing on actually what they are doing, because that is straightforward. You can modify it as you want. So child 1, what it does is that it prints all even numbers in the range 1 to n. So you give it the parameter n, and it will print all the even numbers between 1 to n. Child 2 will print all the odd numbers between the range 1 to n, and child 3 will print square of all the numbers from 1 to n, and child 4 will print cube of all the numbers, right? So let's have a look at the actual code. And this is like working code. You can simply copy paste it, and I have tested it on Linux, on Ubuntu. So you can actually simply copy paste it, and if you have Ubuntu installed, and you are given also the make file, and you can run it and test it for yourself. Okay, so let me walk you through this code. So here, this is just a header file which we are including, number example.h. I will show you what this header file is. And then in the main function, you are just saying that you are expecting an argument. So if number of argument is less than 2, then print this message. Okay, how to use the program, right? Then in the after that, you are actually setting n equal to the input parameter, which is passed to the main program, right? So actually user will specify what is the range from 1 to n, what is n, right? Then we are using these two variables, start and end of type time spec. Why? Because we wanted to measure the time, how long it takes for the program to complete. Okay, before we go ahead, let me just highlight that first we are writing a single threaded program to do the same thing, where we want to where we first want to print all the numbers in range 1 to n, then all odd numbers from 1 to n, square of them and cube of them. So, and then what we want to do is that we measure the time, how long it takes for a single threaded process to do all these tasks. And then what we will do is that we will have a multi-thread version of the same application, and then we measure the time, how long it takes now for the multi-threaded version to complete all those tasks. So here we are just getting a timestamp, right? And then we are calling these functions: print even number, print odd numbers, print square, print cubes, and then we're getting the second timestamp and storing it an end. And then we are measuring the total elapsed time by subtracting start from end, and then converting it to the nanoseconds. I don't want to go through this solving. You can go to the if you are like curious about what is TV underscore sec and TV underscore nanosec. So these are actually the data members of the of this structure. You can go online and you can check the detail, right? What are the data members out there? So then we are just converting the execution time to long double, so that we have the time in seconds, and then we are just printing the time. Clear? So this is straightforward, and here is your number example.h header file, where we have defined these functions: print even number, straightforward. You are just running a for loop, right? And then print odd number, print squares, print cubes. That's it. And here you have the make file, right? So this was the example of a single threaded application doing 4 tasks. Now what we are going to do, we will launch 4 different threads, and we will assign 1 task to each of them. Now let's see how we can do. So this is now multi-threaded version, right? So first, it is the same header file you are including, not same header file, it is a different one. So because it is multi-threaded number example, so it's mean that the header file I have modified. I will show you what the modifications are, right? So, but for now, let's continue with our main function. So at the start, everything is same. We will get the number of we'll get the n as a parameter from the user. We are defining start and end, and variables seconds and nanosecond. All of them are for the purpose of time tracking. Okay, now here is where things starts changing, right? So we are creating an array of 4 elements of type pthread t. So basically, pthread t is a variable type which you can use to store the ID of a thread. So basically, what happens that when you make a system call to create a thread, so on the successful creation, that system call returns the ID of the created thread, and you can store it in a variable of type pthread_t. Okay. So other than that, we are creating an array of function pointers. So actually, it is an array of type wide static, so wide type pointers, and we are initializing it with the name of the 4 functions, like print even number, print odd number, print squares, print cubes, right? So we are just making an array of function pointers. Then we have a variable of type pthread attribute. So why we will use it? We will use it to set the attributes of the threads which we are going to create. So basically, whenever you create a new thread, you first need to specify the attributes which you want to set for that newly created, which you are going to create now, right? So here we are saying that, okay, initialize this variable, right? So we are just using this function pthread_attribute in it, and this function is provided to us by the pthread library. Where have we included the pthread library? In this header file, and we will see that header file later. So here we are initializing the attribute structure with the default values, and then we are doing the time stamping here. So we are getting the start time, and then we are saying, okay, now run the for loop, because we want to create 4 threads, so we are running it for 4 times. And in each iteration, we make the function pthread create, which is a library call, and it is actually, since the library is implemented at the kernel level, so it turns into a system call. So this function, a system call, actually takes 4 parameters. First is the address of the thread, address of a variable where you are going to store the ID of the thread that will be created, right? And remember, we have an array here, right? So we are saying that, okay, store the ID of the first thread in the first element of that array, TID. And store the ID of the second thread in the second element of that array, TID, and so on. And then we are saying that initialize all the threads with the same default attributes, right? So we are passing the address of this. So we are passing the address of this attribute variable. Third, remember, we in pthread library, when you launch a thread, it executes a function. So here we are specifying that function which we want that thread which will be created to execute. And how we are specifying the function? By using the function pointer array. So we are saying that tell the thread which you create, the first newly created thread, tell it to execute the print even number function, right? Because I is equal to 0 will point to the first function pointer. The second thread will execute after being launched. It will execute print odd number. The third will execute print squares, and fourth will will run the print cubes. And the last parameter is the arguments which we are going to which we want to pass to the function that the thread will execute, right? And to all of them we are sending the n, which is like the range 1 to n, right? Please stop me if you don't understand anything here. Okay, so the same file is continued here. So here we just created all the threads, and now the main thread, it is going to wait for all the children threads to complete their execution, and only once all of them are completed, only then the parent thread will continue its execution. So how we specify that the parent will wait for the children by using this library function pthread join. Again, remember, because library in the Linux is implemented as a kernel library, so this library call will convert into it will actually trigger a system call, right? So here we are saying that the parent thread want to wait for which children thread, which has this ID stored in TIDI. So actually we are saying, okay, we wanted to wait for the first thread and second thread and third thread and fourth thread. So it is going to wait for all four threads to complete. Okay. And this is exit status. So if here when we are saying null, so we are saying we don't want to save the exit status which is returned by a child thread, right? So let's say when the child thread 1 will complete, so if we it will return us an exit status. If we want to store it, so here we can pass a variable, let's say the address of a variable, let's say I name it as status, right? But definitely I first need to define that variable, right? Somewhere in the program. So once all of them will be completed, then the parent thread will reach here and will get the timestamp and store it in end. And then rest of the things are same. We are just subtracting end from the start to get the total time elapsed. And then here we print the execution time. Okay. Any questions? Okay, so let's now have a look at the modified header file. So remember I said that we have modified the header file. How we have modified? First, by including in the header file, in the number example header file, another header file pthread.h, which is needed if we are going to use the pthread library in our program, right? What are the changes we have made in the header file? Uh, Everything else is same. The only thing is that when we are done with the when we want a function to be like done with its job, after that we are saying pthread exit 0. Remember, these functions will be executed by threads. So this one will be executed by, let's say, by thread 1, this will be by thread 2, thread 3, and thread 4. So we want those threads to terminate themselves once they are done with their job, right? So because why? Because parent is waiting for all these four threads to complete, and only then parent can continue. If these threads never say pthread exit 0, or let's say if they get stuck in infinite form, infinite loop, then parent will never be able to continue, right? And again, this is the makefile, almost same makefile as we have seen for the single threaded program, with a minor difference that this time when you are compiling, you need to specify that you need to link the pthread library, right? Otherwise, otherwise the library will not be linked into your file, into your executable file, and you will not have threading mode available. Any questions? No? Okay. Uh, then this take us to our next topic, thread local storage. What is thread local storage? Let me try to explain using an example. Okay. So let's have a look at this code. Let's start from the left side. So here we have like bunch of header file included. Among them is one pthread.h, because we are going to use the pthread library. So we have a global variable my ID, and then we have a function set or get my ID, right? So so here in this function, what we are doing is that whenever we pass an ID, so my ID is set, global variable is set into the equal to the parameter, and then the thread that is executing this function will sleep for some time, like for 1 second, and then it will print its ID, right? Now let's have a look at the main program, right? So main function. So in main function, what you have, since we are going to create two threads, so we create an array of two elements of type pthread to hold the IDs of the threads, which will be create. Then we have a variable attribute of type pthread attribute so that we can use it for initializing the threads with the default values. So here we are initializing that structure with all the default attributes, same thing as which we have done in the previous example. Then we are defining a function pointer. We are like initializing the function pointer array and setting it to the two functions which will be called. So remember here that both elements of this function pointer array are initialized by the same value, set get my ID, set get my ID. Why? Because we are launching two threads, but we want both of them to execute the same function, right? And we are initializing IDs, an array of IDs equal to 1 and 2. So actually what we are going to say is we want to set the ID for first thread equal to 1 and the second thread equal to 2. Remember, these are our user level IDs. These are not the same IDs which are returned here by the, which will be stored here and which will be returned by the kernel, right? As a result of pthread creation, right? So these are the like parameters which we will pass to these functions, because remember these threads are going to invoke set get my ID, and if you look at the definition of set get my ID, it gets an input parameter ID. So what parameter we will pass? We will pass an input of ID 1 for the first thread and input of ID 2 for the second thread, right? Now, here what we are doing, we are running a loop to create the threads. So we are saying pthread create. We are passing the first element of the TID array to store the ID of which will be returned for after the creation of the first thread. We are specifying this address of this attribute, which we have attribute structure, which we have already initialized. And then here we are passing the function pointer I, which is basically the function point, which is basically pointing to this function, right? So we are saying that thread 1 will execute this function. However, the ID or the input parameter which we want to pass to this function for the first thread is IDs. For the first thread, I will be 0, so it will basically be 1. So we are saying that ID set this parameter equal to 1 for the first thread, right? For the second thread, everything will be same, but the only difference will be that the parameter which will be passed to this set my ID function, it will be equal to 2, right? And then we are saying now that parent will wait for the two children threads to complete their execution, and then it will return 0, right? By the way, I think here I need to put pthread exit, right? So maybe I can make this correction right now, otherwise, I will forget later. I can simply copy paste from here. Okay. So now when we now if we run this program, right? If I run this program which has the main function, definitely will create the threads, but and both of them will execute this code, right? So first thread will get here 1, right? And the second thread will get here 2, right? But when they print the statement, both of them say my ID is 2, my ID is 2. While I was expecting that the thread 1 will say my ID is 1 and thread 2 will say my ID is 2, right? So by both threads have same ID, right? They both have same ID because what can happen is this. So let's say this is your thread 1, right? So, and it starts executing, and here you have, let's say, thread 2, right? So let's say thread 1 starts executing, it sets my ID equal to 1. I am writing only my I because I don't want to go to the notepad because OneNote, because it takes time, right? So I'm putting my ID is equal to 1, and then this thread is put to sleep, right? So if it is put to sleep, it's mean that it is not executing. Now, when the thread 1 is sleeping, let's say thread 2 starts executing. If the thread 2 start executing, what it will do? It will set my ID equal to 1. Remember, my ID is a global variable, right? So it will set my ID equal to 2. Okay. And let's say thread 2 continues executing, like let's say it sleeps, and while it is sleeping, thread 1 comes back and it does the printf statement. So when it does the printf statement, it will print my id is 2. Why? Because my id variable has been updated by thread 2. And when after that, and then it will complete its execution, and when thread 2 will wake up, it will also print the printf statement, and it will say my id is 2, right? So this is problem. Why this is problem? Because I am passing values of, I'm passing different parameters to both threads, to the functions which are executed by the both thread, but I'm passing different parameters. But those parameters are not making any difference. Why? Because they are using the global data, right? They are setting the global value of the global data variable is set to the parameter, right? So this global data is shared among all the threads, right? Now, how can, let's say I want to say that no, I don't want them to have the same, to share the same global data. I want them to have their own my ID, own version of their my ID, so that their IDs are different, right? How can I do that, right? So I can do that by defining thread local storage, which means I can do that by specifying that my ID, don't treat my ID as a global or shared variable, treat it as a thread local storage, such that, which means that each of the thread which accesses this variable will have its own copy of the variable. So if one thread changes the data, it will changes only for its own copy. It will not affect the data for the copy of the other threads. Am I clear? Okay, let me check the time. I think you guys have quiz today. 2 minutes are left. So let me go through it quickly because it's not a big deal. So how to ensure that both threads do not share my ID? By having private copies or unique copies of my ID for both threads, and this is known as thread local storage. So how you can specify that, how you can tell that I want I want to make my ID a thread local storage, or I want every thread to have its own unique copy. So for example, in C11, or like C11 version of C language, you can make thread local storage by using a class specifier, right? Uh, So if you specify a variable as a thread local storage, then every thread will have its own copy. And how you do that? Here is the quick way. Everything else in this program is same. Everything else is same. We are not changing anything. Only thing we are changing is here is by putting this specifier underscore thread underscore local int my ID. Now what will happen? That there will be two copies of my ID, one for thread 1, second for thread 2, and they will not be able to be overwritten by anyone, by the other thread. So this time when you will run the program, my ID is 1, and you will see the output my ID is 1, my ID is 2. Okay. So here the C111 is actually the language is providing the support to use the thread local storage. So what if a language, for example, unlike C11, some language does not support TLS, you don't have a thread specifier in a language. So what you can do, for example, in older version of C, so you can use the library support. For example, your pthread library allows you gives you a mechanism to define that I want to use this particular data as a thread local storage. And for that, you need to use this function pthread key. We are not going to use that, but I mean, I just wanted to give you a reference that if you are interested, you can go and read what is pthread key create and how. Okay. So let's stop here. Do you have any questions? No?
That makes sense. And
Okay.
do we have a quiz today?
Yeah, yeah. Please go ahead. And if you have any questions, I will stay even after the class time. Okay. So go ahead and do your quiz.